Why do we tune our instruments the way we do, and why 12 notes? There are many videos on this topic, but I'm going to show you the explanation that you may never encountered before. The creation of tuning system, or system that dictates what pitches to use when playing music, is complicated because you don't want to make music with just a couple of notes. And as you increase their number, conflicts arise in the way how they combine with each other. So finding a successful combination of pitches has been the cause of debate and has led to the creation of many different tuning systems across the world, each having its characteristic strengths and weaknesses. In the West, 12 common notes appeared as the most practical way to access useful musical intervals. Let me briefly explain what do I mean. In theory, there can be infinite number of intervals because pitch is continuous, but majority of people will agree that some intervals stand out amongst the others as the most pleasing sounding and therefore they should be used in music. Useful observation is that frequencies of notes comprising such intervals relate to one another as simple ratios. Those intervals are perfect octave, ratio 2:1, perfect fifth, 3:2, fourth, 4:3, major 6, major third, minor 6, and minor third. So now we have several notes and you can use that as tuning system. But it has gaps that can be filled with following intervals. On its own, they don't sound very pleasant, but they come very handy when writing melodies, for example. And with time they found the way into harmony as well, as they allow for many possibilities for play of tension and release, which is one of the most important aspects in music. Table to the left is color-coded, so you can see that the simpler the ratio, the more consonant the interval is. An octave is so consonant that it is thought to be the same note. That is called octave equivalence. Tuning system based on simple ratios is called just intonation. Let's zoom on it. Here we can see all the notes of just intonation calculated from the root C on horizontal scale. We see that they are not equally spaced. That makes just intonation somewhat impractical. For example, it is a problem for instruments such as a piano, because if tuned to just intonation, they can perform harmoniously only relative to a certain key center. In this case, it is C. A long time ago, people noticed that our ear forgives slight deviation from perfect ratios, allowing for temper tuning systems, such as modern 12-tone equal temperament, in which pitches of notes are slightly shifted to be equally spaced. That sacrifices purity of harmony of simple ratios, as those most pleasing intervals are now a little bit more dissonant, but it improves practicality. And history shows that this is the trade-off that people are willing to make. All of that can be summarized as follows. Because observation shows that the most consonant musical intervals correspond to simple ratios, the issue of tuning can be handled with mathematics of simple ratios and tempering. What I've been talking about is a pretty classical thing. You may have heard it before. Defining consonance and dissonance through the simplicity of ratio is very common in literature on tuning theory, like, for example, in the book Arithmetic of Listening by Kyle Gunn. One definition of consonance, the one used in this book, is that two pitches are consonant when their vibrations can be related by small numbers. But is it always the case that simple ratios sound consonantly? Let me demonstrate how perfect octave, 2:1 ratio, can sound dissonant. And by dissonant, I don't mean dissonant in the sense of context of music piece, or in the sense of tension and resolution. From now on, by the word dissonant, I will mean instantaneous or perceived dissonance, or what contributes to the observation that on its own, octave sounds more consonant than tritone, or, you know, that thing that makes us say that this guitar is out of tune. To clearly demonstrate how it is possible, I will use two synthesized sounds. One is first 6 partials of harmonic spectrum, and another one is 6 first partials of stretched harmonic spectrum. What do I mean by that? Each time you play a note, a bunch of frequencies is being excited. Those frequencies are not random but follow a law called harmonic series. Each partial is a whole number multiple of fundamental frequency. Spectrum that follow harmonic series is called harmonic spectrum. Okay, so if this is harmonic spectrum, that portion of it will be our first sample. And the second one is just like it, but stretched in frequency according to this formula. So the first partial will be 2.1 times the frequency of fundamental, second 3.24, and so on. Now let's play an octave with both spectrums to see how it sounds, and look at the spectrogram to see what is happening. First one is normal harmonic spectrum. I will play A equals 220 Hz and A an octave higher, 440 Hz. Sounds like an octave. And now stretched harmonic spectrum. You can see that I am playing the same pitches, so the ratio between them is exactly 2:1, as it should be. But they sound kinda dissonant. It is because you can see on the spectrum the partials of notes don't align with each other. That misalignment causes beating between these partials. Beating is a phenomenon that happened between two sine waves of close frequencies. Here we have two sine waves of 300 Hz and 310 Hz. If I sum them, the resulting waveform will be following. The amplitude of it oscillates with frequency of 10 Hz, which is the frequency difference between sine waves. And this is how it sounds. Now let's sweep sine waves in frequencies to hear the range of how beating can sound. The graph you see on the screen is analogous to the one taken from the article by Plomb and Leveld, Tonal Consonance and Critical Bandwidth, only flipped upside down because I plot dissonance and they've plotted consonance. Coming back to our stretched octaves. Because our inner ear decomposes sound into spectrum, watch my previous video, we perceive all those sine waves individually, and the beating that happen when partials misalign. And that beating we perceive as dissonance. Important to note is that dissonance is much more complicated phenomenon that depends on other things as well, as beating alone doesn't explain it all. For now, I'll just mention that according to recent article Simultaneous Consonance in Music Perception and Composition, there are three major mechanisms contributing to our perception of dissonance. It is spectral interference, or the one I'm talking about in this video that relates to beating, periodicity, or how close the spectrum is to harmonic spectrum, and cultural conditioning, or what we've learned through our life to sound consonant or dissonant. Okay, so if in case of stretched spectrum, dissonance is caused by misalignment of partials, maybe we can stretch the tuning to mitigate that misalignment. And I did just that in that tuning file, so the octave, or let's call it pseudo-octave, is now 2.1 to 1, or 210 Hz for higher note and 100 Hz for lower. All the rest of 12 notes are equal divisions of that pseudo-octave, or 12 root of 2.1. Let's listen to that. Now it sounds like an octave. If I play for release with stretched spectrum in related stretch tuning, you will recognize the harmony and the melody, though of course the timbre sounds kind of weird and quite alien, and maybe the dissonances are not quite the same, but still it's very recognizable. And now let's listen how it sounds played in the same stretch tuning, but with harmonic spectrum, with the usual spectrum that we used to hear. and it sounds really bad. And you can see on spectrogram I colored harmonics of left and right hand notes in different colors. So you can see when tuning corresponds to spectrum, harmonics align with each other, and when they don't, they clash and cause dissonance. I think it clearly demonstrates how spectrum or timbre of sound can affect tuning. If you want to experiment with this yourself, I put down long links to these samples and tuning files in the description below. You may wonder if there are any real-world examples of how spectral structure affects tuning. Not in synthesizers with some weird-ass sounds, but something closer to reality. And yes, there is. Similar stuff happens in the piano. Let's make an experiment. Let's analyze a spectrum of a low piano note. Let it be C1. I'll load a sample that I made into Audacity. Let's look into it. Here's the sample. This is how it sounds. And then I'll make a selection and plot a spectrum. Now this is the spectrum of the note. The frequency of C1 is 32.7 Hz, so this is the fundamental. In Audacity, the cursor snaps to nearest peak and shows the frequency value here. So now I'll go through several partials and write down their frequencies into Excel spreadsheet. Okay, so it is done. These are the frequencies of partials. In the second column, we can see the calculation of ratio of a partial to fundamental. As we discussed before, the frequencies of partials should follow harmonic series. So these ratios should be whole numbers like in third column. But we can see that there is a deviation of a piano partials from harmonic series, and that deviation is calculated in fourth column. And so on average it is about 1.7%. But this way only for the low notes. Notes couple of octaves above are much closer to harmonic series, and I already prepared tables to show you that I performed the same thing in Audacity with C2 and C3 notes, and we can see that deviation falls to 0.68 for C2, or the octave above the C1, and to 0.09 for C3. But we still tune piano to 12-tone equal temperament, right? Almost. Piano tuners actually stretch octaves a little bit, so the low octaves in the piano are not 2:1 as they should be, but in our case 2.03:1 for the octave between C1 and C2. I won't get into physics why it is happening. In short, it is because of stiffness of the low piano strings. They are too short and too thick. If you want to know more details, you can watch this video where the guy shows exactly why it is happening by modeling string in MATLAB. If the spectrum that follows harmonic series is called harmonic spectrum, the spectrum that does not follow harmonic series is called inharmonic spectrum. The amount of deviation from harmonic spectrum is called inharmonicity. The more inharmonic the sound is, the more metal-like or bell-like it sounds. It can even sound kind of dissonant by itself when only one note is being played. The inharmonicity of the piano is very small, though big enough to influence the tuning, but it is still quite subtle. Much bigger inharmonicity was happening with the example of synthesized stretched spectrum. That's why the effect on tuning in piano is so much more subtle. I won't demonstrate it in the video, but you can try it for yourself by downloading Piano Tech and comparing equal temperament setting with flat. Pay attention to low notes and high notes and play with octave stretch slider. You will be able to hear that in flat tuning, high notes are a little bit flat relative to low notes. Also, Piano Tech manual has some details on that stuff in sections about octave stretching and string length. The first one to suggest that musical tuning arises from spectral structure of sound was famous physicist Hermann Helmholtz, who in 1863 published his foundational work on the sensations of tone as physiological basis for the theory of music. He theorized that we perceive sound in spectral domain, and because vibrations of strings or other musical bodies consist of many individual pitches, partials of a sound, it is interaction between partials of different notes, more specifically beating of nearby partials, that contribute to our perception of dissonance. The plump and leveled article that I mentioned when I was talking about beating is a continuation and experimental evaluation of Helmholtz's approach. The graph of perceived dissonance that they experimentally obtained can be used to explain why observations show that simple ratios correlate with our perception of dissonance. In my previous video, I was talking about the mechanism of how people hear sound. In short, the part of inner ear called cochlea decomposes sound waves into individual partials that are sent to the brain in parallel. That system has finite resolution and can be modeled as a collection of bandpass filters. Notion of critical bandwidth relates to the bandwidth of these filters. If two sine waves are very close to one another, we won't be able to distinguish between them, and we will hear beating. If sine waves are far enough to occupy different bands, we will perceive two distinct pitches. This graph I showed you from plump and leveled article is related to the critical bandwidth. The peak of dissonance happens at about 1/4 of critical bandwidth and then steadily decline until two individual sine waves are perceived. Critical bandwidth depends on frequency. At low frequencies it is wider than at high frequencies. That will influence this graph the following way. So our ear is better at distinguishing pitches at higher frequencies. This is the reason why major third sounds fine in higher registers and kind of muddy and dissonant at low registers. As we recall, when we hit a note, we excite a bunch of different frequencies. When we hit two notes, their partials start to interact with each other. Some are close and cause beating, others are perceived separately. Each pair of sine waves contributes to the perceived dissonance in the way that it is described by this graph. So, if we sum all contributions between all the pairs of partials, we will get the value of perceived dissonance of a complex tone that is two notes. And we can do it for any musical interval and any spectrum of musical instrument. So check this out. Let's divide an octave into 1,000 equal parts. That will give us 1,000 different intervals. And calculate dissonance value for each one of these 1,000 intervals by summing contributions from every pair of partials in this interval. And let's use 6 first partials of harmonic spectrum for calculation and plot it. We will get this graph that has these local minimums of perceived dissonance that appear because of interaction of individual partials in spectrum of two notes as they sweep across the span of one octave. Those minimums appear exactly at simple ratios, giving us the most consonant intervals in just intonation. These intervals stand out among others as the most consonant and therefore play a major role in music production. You can call it natural tuning for this spectrum, or better call it related tuning, meaning that it is related to spectral structure of a single note. In that sense, just intonation is related tuning for harmonic spectrum. You may wonder why anyone need to go that far to get to simple ratios. And it is because this approach can be used for inharmonic sounds, where the simple ratios, as I showed you before, may not work. In case of stretched spectrum, it will give stretched just intonation. Or like in my first video, in which I claim to solve Benedetti's puzzle, what I did is I synthesized spectrum with following partials that give the following dissonance curve, where minimums of dissonance lie on the notes of 12-tone equal temperament rather than simple ratios. So 12-tone equal temperament is related tuning for this spectrum, just like just intonation is related for harmonic spectrum, thus ensuring maximum consonance in the sense that there is no beating, and pitch stability when playing Benedetti's puzzle. Another benefit is that this approach can be used to understand music of other cultures that utilize inharmonic sounds, such as gamelan music tradition, which is traditional Indonesian music. It is performed on metal plates that have highly inharmonic spectrum and are tuned very differently to Western tradition. Precisely to minimize beating that would have happened if they were tuned using simple ratios. And lastly, it can be used to come up with new instruments that utilize coupling between tuning and spectrum, like hyperpiano that performs harmoniously in 10-tone equal temperament, that is quite dissonant if played with harmonic spectrum and don't approximate any of conventional intervals from just intonation. I wanted to talk more about gamelan music and hyperpiano, but I think this is material for another video, as it is time to wrap it up. In conclusion, I hope I was able to demonstrate that natural world gives us possibilities to go beyond harmonic series for music production, and that rational numbers and simple ratios aren't fundamental reason to construct a tuning system with, and that manipulations with spectrum of instruments may be another dimension through which we can control dissonance, maybe as alternative to tempering or to access new tunings. However, it is a long-standing tradition to use simple ratios to define consonance and dissonance, as well as explaining the reason behind tuning systems that we use. But one should always remember that such an approach is applicable only for harmonic spectrum, which is definitely special for humans, as our voices are harmonic and therefore our brains are tuned to look for it. But there is no objective reason why we should stick to it exclusively. The majority of all possible sounds are inharmonic, and they may hide inside a harmony that is waiting to be discovered. In the description you will find links to books and articles on that topic, as well as some materials that I used for this video, such as samples of spectrums and corresponding tuning files. Post a comment if you think that this topic is interesting and if you want to know more, as well as any questions that you may have. These videos are tough to make and it does require some expenditure, so consider supporting on Patreon or purchasing my music on Bandcamp or anywhere else. It is not very experimental, as it does not yet implement all this dissonance stuff that I'm researching, but give me some time, because it will. So like, share, subscribe, and until next time.